Good evening, everyone.
Evening, sir.
Good evening. How are you?
Good, and how are you?
I'm also good, thank you. Yeah, guys. So please take a note that the recording has started, and yeah, welcome to today's meeting. So even today, we will still be focusing on centrifugal pumps graphs. So um, I can see that you have this problem here, that and want us to actually, or that needs us to actually go through it. Yeah, so I'll go through this problem here, and then after that, then I'll dive into the affinity laws. Yeah. So I will be drawing, like for example, question one. I will be drawing the graph manually and also using Excel. Yeah, so I will be drawing the graph of question one manually, meaning using a graph paper, and then also using Excel after that. So yeah, without any waste of time, we will start with this problem because we already went through the centrifugal pump graphs. So I'll start with this problem, and then after that, we will go through affinity laws. Yeah, so without any waste of time, let's start here. In this question one here, it's saying during a laboratory test on a centrifugal pump, a characteristic curve for the pump was obtained that is given by the following formula or the equation. So you can see here that the head is equals to 4.5, actually 45.5, sorry, and then minus 200 times the volumetric flow rate, and then minus 4,000 times the volumetric flow rate squared here, where H is the head in meters produced by the pump, meaning H is the height of the pump, and Q is the discharge in cubic meters per second, or Q is the volumetric flow rate in cubic meters per second. And then here they're saying that the pump is then used to pump water through a static head of 18.5 meters. Static head is the change in elevations through a pipe with a length of 760 meters and also a diameter of 325 millimeters. So you must take here the losses because of elbows and accessories to be 30 meters of the pipe. Then assume that the friction factor is equals to 0.07, and then calculate the following. Firstly, you must calculate the discharge, which is the volumetric flow rate. And then after that, you must also calculate the head of the pump, meaning the height of the pump. And then lastly, you must calculate the power required by the pump if the efficiency at the operation point or at the working point is equals to 67%. Okay, so since here we're not given the readings of the volumetric flow rate, since here we're not given the readings of the volumetric flow rate, so we'll have to then come up with our own volumetric flow rate readings in order for us to be able to generate the readings of the head of the pump or the characteristic curve, as well as the system curve as well as the system curve. So yeah, last year we had this same problem, and then I remember I used equidistance scale of 0.01 for the volumetric flow rate. Yeah. So I will be using the very same equidistance scale to generate these readings of the characteristic curve as well as the system curve. Yeah. So without any loss of time, let's start. So firstly, obviously, you have to draw a table that will have the volumetric flow rate readings, the characteristic curve readings, as well as the system curve readings. So the volumetric flow rate, the characteristic curve, as well as the system curve readings. Yeah. So since we'll be using the equidistance scale of 0.01 for the volumetric flow rate, let's have the maximum reading of, let me say, 0.05. And then, of course, the minimum reading for the volumetric flow rate will be 0. So meaning that these readings, they mustn't be below or 0. They mustn't be, no, they mustn't be below 0.05. And what am I saying? They mustn't be below, yes, they mustn't be below 0 meter cube per second. And also, they mustn't be above 0.05 cubic meters per second, since I decided to say let the maximum volumetric flow rate be 0.05 and the minimum one be 0 cubic meters per second. So meaning that on our first row, we'll have here the readings of the volumetric flow rate measured in cubic meters per second. And our first volumetric flow rate that we will have will be 0 meter cube per second. That will be followed by, since I'm using the equidistance scale of 0.01, so that will be followed by 0.01. And then thereafter, I'll have to add 0.01 on this reading. So that will give me what? 0.02. And then from here on 0.02, I'll add 0.01 again, since I'm using the equidistance scale of 0.01. So that will be 0.03. And then followed by, of course, 0.04. And lastly, 0.05. So let this be my readings for the volumetric flow rate. And then from here, row number 2, I'll have the readings of the head. I'll have the readings of the head in meters. So in order for us to be able to generate the readings of this head or the characteristic curve, we'll be using this equation provided here. We'll be using this equation provided here. So that equation is given by the head is equals to 45.5, and then minus 200 multiplied by Q, and then lastly minus 4,000, then multiplied by Q squared. Yeah, so from here, to find the readings of the characteristic curve, which means we'll have to take these readings of the volumetric flow rate and plug them in this equation respectively in order for us to be able to generate the readings of the characteristic curve. For example, the reading or the first reading of the head will be equals to or will be given by 45.5 minus 200 into 0 because of first volumetric flow rate is equals to 0 cubic meters per second. Then minus 4,000 and then multiply by into 0 cubic meters per second and then squared. So meaning that our first volumetric flow rate here will be equals to 45.5 meters. Will be equals to 45.5 meters. Then, in order for us to find this reading here, which means we'll take 0.01 as the volumetric flow rate and substitute with it here. So, which means that the second reading for the head will be equals to 45.5 minus 200 and then multiply by into 0.01 and then minus 4,000 and then multiply by 0.01 and then squared. So meaning that the second reading of the head is equals to 43.1 is equals to 43.1. Okay, for the third reading, of course, the volumetric flow rate will be equal to 0.02. So meaning that where you see Q, you just have to simply substitute with 0.02 in this equation. And then you'll be able to get 39.9. 39.9. Okay, so the reading here will be equals to 35.9 since the volumetric flow rate is equals to 0.03. And then since the volumetric flow rate here is 0.04, the rating for head will be equals to 31.1 meters. And lastly, volumetric flow rate is 0.05. So that will be equals to 25.5. If you like, you can continue. Maybe you can let your reading maximum be 0.1, for example. I'm just giving an example. Then you can continue with 0.06 till 0.1. Yeah, I'm just giving an example. So yeah, that's how to find the readings of the characteristic curve. Then from here, we must also generate the readings of the system curve. We must also generate the readings of the system curve. So the system curve, firstly, in order for us to generate the readings of the system curve, we'll have to use, sometimes they will give you the equation of the system curve. Yeah, but this time around, we are not giving the equation of the system curve, but we are given the data to utilize in order for us to be able to find the readings of this system curve. So we've got the equation, the general equation of the system curve. So it's given by its system is equals to the change in height or the change in elevation, and then plus the formula for the major loss, which is given by the friction factor, then multiply by length, multiply by volumetric flow rate squared, and then divided by 3.03 times a diameter exponent 5. So yeah, so this is the general equation of the system curve. And then now we're going to use this data. This data provided from this paragraph to generate the equation of the system curve. So like I told you, the steady state is the change in elevation head, 18.5 meters. So meaning that this system here will be given by 18.5 meters, then plus the magnitude of the friction factor. So the friction factor is equal to 0.07 here. And then, okay, plus 0.07, the friction factor, and then multiply by the length of the pipe. So remember, the total length of the pipe is given by the straight pieces of the pipe length, the straight pieces of the pipe length, or the length of the straight pieces of the pipe, then plus the plus the elbows and accessories, which are the pipe fittings. Yeah, I wanted to say pipe fittings, plus the length of the pipe fittings. So the total length of the pipe fittings, which involves or includes the elbows and accessories, is equals to 30 meters, meaning that the total length of this pipe will be 760 and then plus 30 meters. So meaning that the length here will be equal to 760 plus 30 meters. Then multiply by the unknown volumetric flow rate. Let's leave it there. Then divided by 3.03 multiplied by the diameter in meters, then exponent 5. So the diameter is given in millimeters here, and it's equals to 325 in magnitude. So we must convert this to meters. That's 325 millimeters to meters. Simply, we're going to take 325 and multiply it with 10 exponent negative 3. Or alternatively, you can take this 325 and divide it with 1000. And you will be able to get 0.325. You will be able to get 0.325 meters. All right, and then all exponent 5. So therefore, the head system or the system head will be equals to here 18.5 plus 0.07 times into 760, then plus 30, and then divided by 3.03, and then times 0.325, and all exponent 5. Okay. Wait, actually I wasn't supposed to include this 18.5 because it's not part of this expression. Sorry. Let's leave 18.5 here as it is. And then the total of this expression here, which means it will be equals to what? Let me start afresh. 0.07 times 760 plus 30. And then all divided by 3.03. And then times 0.325, all exponent 5. Yeah. Right, so that is equals to 5033, let's just say 449, and times q squared, unknown volumetric flow rate squared. Yeah. So meaning that we will be using this equation of the system head to find the readings here of the system curve, Okay. Like the characteristic curve, in order for us to find the system curve readings, we will be using this volumetric flow rate readings, and then when we see the volumetric flow rate, then we're going to substitute with them. So meaning that the first reading here for the system curve will be equals to 18.5 because Q here is equals to 0 cubic meters per second. So the first reading for the H system will be equals to 18.5 meters. Okay, and then this is followed by the second reading of the system curve, which will be what? 18.5 plus 50.449 and then times 0.01, then whole exponent 2. All right, so that is equals to 19 meters. And then the third volumetric flow rate, actually the fourth volumetric flow rate, is equals to 0.0. Yeah, no, the third, yeah, I was right. The third volumetric flow rate is equals to 0.02, 0.02. So that is equals to, let's just say 20.5 or 20.51, doesn't matter. And then the fourth volumetric flow rate is equals to 0.03. So that is equals to actually 23. And then this is followed by volumetric flow rate 0.04, which is equals to 26.55 or 56. 26.6 or 26.55. Yeah. Lastly, the volumetric flow rate is equals to 0.05, and that is equals to 31.1 or 31 meters. So yeah, so that's how to generate the ratings of the characteristic curve as well as the system curve. Do you guys have questions? Okay, so let's move from here. Because the question says, I hope you guys are able to hear me. So from here, because the question says we must find the magnitude of the volumetric flow rate, the head, as well as the power, we must first draw the graph of the centrifugal pump. We must first draw the graph of this centrifugal pump, which will be the graph of the head versus the volumetric flow rate. Okay, let me quickly attach the graph paper.
Meneer, a quick question.
Ebo.
The calculation say you have to do it the Aungwala test or you have to do it on the site and then Ungwala the answers.
No, you have to write them on your what we call answer paper. Yeah.
Okay, all right.
Yes. Don't just write them aside. Yeah. You have to write them on the answer sheet. Yes.
So on that question, sorry to interject, does it mean in the formula, let's say I'm utilizing the pump characteristic, does it mean I have to show all the substitution of the volumetric flow rate?
Oh, no.
Okay.
Yeah, there's no need for you to
As long as the
show all
table
the
is,
substitution. Yeah.
as long as the table has been completed.
Yeah.
Okay.
Okay. Okay, so here's the graph paper, like I said. This will be the graph of the head versus the volumetric flow rate. So it will be the graph of the head versus the volumetric flow rate. So volumetric flow rate, of course, is in cubic meters per second. And then the head here is in meters. Please switch off your mic. So yeah, let's go back to this table. Let's go back to this table. So meaning that, okay, by looking at these readings of the characteristic curve and the system curve. So the maximum number that we have here is 45.5, or let me say the highest number that we have is 45.5, and then the lowest one is 19. The lowest one is 19. So let's use equidistant scale of let's use equidistant scale of 10. Yeah, let's use the equidistant scale of 10. So meaning along y-axis we'll have 0, then 10, 20, 30, 40, yeah, just like that. Up until, let's say, let the maximum number along y-axis be 50, because here we've got 45.5, yeah. So let's have equidistant scale of 10 along y-axis. Then, yeah, our minimum number will be 0, and then our maximum number will be 50 meters. And then this means that our first horizontal measure grid line will be at 10. Okay, here is 0. So our first measure horizontal grid line will be at 10. So, okay, let's have in between 0 and 10, let's have minor grid lines, horizontal minor grid lines, or let's have 10, not 10, let's have 5. Yeah, 5 minor horizontal grid lines between 0 and 10, or within the equidistant scale. So we'll have 0, and then 1, 2, 3, then 4, then 5. So let this be our 10 meters, which is our first major grid line. And then, of course, the number that comes after 10 is 20. So between 10 and 20, we'll still have 5 minor horizontal grid lines. So meaning that we'll count from 10. So we'll have 1, 2, 3, 4, 5 minor grid lines. Then which means here we'll have 20 meters. And then from 20, we'll have 1, 2, 3, 4, 5 minor horizontal grid lines. And then that will be 30, of course, after 20. And then after that, we'll have 40, of course. And then we'll have 1, 2, 3, 4, 5, between 40 and 30. We'll have 5 minor horizontal grid lines. Lastly, like I said, let's have a maximum reading of 50 meters along y-axis. So meaning we'll count from 14 now, and then we'll count 5 major horizontal grid lines going up. 1, 2, 3, then 4, then 5. So this will be our 50 meters. 50 meters. So yeah, if you like, you can use an equidistant scale of 5, meaning you have 0, and then 5, 10, and then 15, 20, 25, 30, 35, up until here. Yeah. So, and then let's go back to that table and have a look on our volumetric flow rate readings. You can see that the minimum reading is 0, and then maximum one is 0.05. Yeah, even here, let's use the equidistant scale. No, of course, we have equidistant scale of 0.01. Even here, I want to say, let's have 5 minor vertical grid lines between the major vertical grid lines. Okay, so meaning along x-axis, starting from 0, we'll count 5 minor vertical grid lines going towards a positive x direction, meaning we'll have 0 here, then 1, 2, 3, 4, then 5. So meaning that since we're using equidistant scale of 0.01, this which means will be our first measure, vertical grid lines as 0.01 cubic meters per second, of course. And then from here, we're still going to count 5 minor vertical grid lines towards positive x direction. 1, 2, 3, 4, and 5. So meaning that this will be our 0.02. 1, 2, 3, 4, 5. This will be our 0.03. And then after this, we'll have 1, 2, 3, 4, 5. So this is our 0.04. 1, 2, 3, 4, 5. This will be our 0.05. Then that's it. Now let's analyze our x-axis line of this centrifugal pump graph. Okay, so since within this 0 and 0.01, we've got 5 minor vertical grid lines, meaning that we'll have 0 here, and then 0.02, 0.002 actually, 0 here, 0.002, 0.004, 0.006, and 0.008, then 0.01. Do you guys understand this? So it's 0, 0.002, 0.004, 0.006, 0.008, then 0.01. Are we together? Then this means that after 0.01, we'll have 0.012, 0.014, 0.016, 0.018, then 0.02. Are we together? So meaning that for our minor grid lines, actually minor vertical grid lines, we'll be using an equidistance scale of 0.02. No, 0.002. Yeah, we'll be using an equidistance scale of 0.002. 0, 0.002, 0.004, 0.006, 0.008, then 0.01. Then after that, of course, since we're using an equidistance scale of 0.002 for the minor vertical grid lines, we'll have then 0.012, 0.014, 0.02 here. And then vertically, you can see we're using equidistance scale of 10. And we've got 5 minor horizontal grid lines between 10 and 0. So meaning that we can use an equidistance scale of 2. So we'll have 0, then 2, 4, 6, 8, then 10. And then 12, 14, 16, 18, then 20. Just like that. Yeah. So now, I hope you guys understand this. So now we're going to plot our graph. We are now going to plot our graph. So x-axis and the y-axis. So now let's plot our graph. Let's plot our graph. Of course, to plot our graph, we'll be using this readings here. So let's start with the characteristic curve. We're gonna draw characteristic curve using these readings. So meaning that our first x and y coordinates will be 0 and 45.5. 45.5, 0 and 45.5. So volumetric flow rate, when volumetric flow rate is 0, 45.5 will be where? So since this is 40, 45 is here. Because this is 42, this is 44, then 46, then 48, then 50. So meaning that 45 is here. So 45.5, meaning it must be between 45 and 46. Somewhere here. Between 45 and 46. Next one. The next x and y coordinates will be 0.01. And for the 3, let's just round off to the nearest this one. For the 3. So 0.01 is here. 0.01 is here, and 43. This is 40, 42, then 43 here. Next, x and y coordinates is 0.02. And yeah, 39.9. Let's round off to the nearest. So which means we'll have 0.02 and 40. 0.02 is here, 40 is here. Next, we'll have 0.03 and 35.9. Let's round off to the nearest. So that is close to 36. 0.03 and 36. This is 30, 32, 34, and then 36. And 36, sorry. And 36, no, here. It's 0.03 and 36, yeah. Next one, we'll have 0.04, of course, and 0.04 and 31.1. 31.1 is close to 31 when we're rounding off to the nearest. So we'll have 0.04 and 31. Okay, so 0.04 is here, and then 31 will be here, because this is 30, then 31, then 32. Yeah. 0.04 and 31. Lastly, we'll have 0.05 and 25.5. 0.05 and 25.5. 0.05, this is 20, 22, 24, and 25. 25.5 is in between 26 and 25. Yeah. 22, 24, 25, then 26. Yeah. Now let's join these dots. No. Yeah. So this is our characteristic here. This is our characteristic here. Now, let's draw the system curve. Or do you guys have questions before we proceed to the system curve? Okay, let's move. System curve, of course, we'll be using to have system curve, of course, we'll be using the volumetric flow rate readings as well as the system head readings. So meaning our first x and y coordinate will be 0 and 18.5. 0 and 18.5. Volumetric flow rate, or one volumetric flow rate is 0. And the system head is 18.5. The system head is 18.5. This is 20, this is 18. 20, 18. And then this means that this is 19. So meaning that our first point or dot of the system curve will be somewhere here in between 18 and 19, 18.5. Next, we have got 0.01 and 19. So that is 0.01, then 19 is here. Followed by 0.02 and 20.5. 20.5 is in between 20 and 21. 0.02 and 21.5. 0.02 and 21.5. 21.5, 21.5 here. So this is 20, and then 21, and 21.5, then 22. Okay, so lastly, not lastly, the next x and y coordinates will be 0.04 and 56.55. Let's round off this to 26.6. Let's round off this to 26.6. So which means we'll have 0.03 and 26.6. So 26.6 is in between 26 and 27. 0.03 and 26 is here. And then this is 27, which means let's say 20, 22, 24, then 26, then 27. Yeah. Then the next x and y coordinates will be 0.04. Wait, no. The next x and y coordinates will be 0.05 and 31.1. Let's round off this to 31. 0.05 and 31.
Meneer,
Yebo.
code 3 is 26 or is 23?
Let me go back. Huh? Oh, yeah, you are right. Thanks. It's 0.03 and 23. Yes. Thank you. 0.03 and 23. Okay, let me just shift this to 23 somewhere here. So 0.03 and 23. Yeah. So which means that the next one will be 0.04 and 26.6. And 26.6. 0.04 and 26.6. So 26.6, it must be between 26 and 27 actually. 26 and 27. Yeah. So 22, 24, and 26. Yeah. So 0.04 and 26.6. Lastly, we'll have 0.05 and 81. 0.05 and 81. So this is 0.05. 31, 31, 31, 31 is somewhere here. Okay. So now we just have to join this. So you know that sorry. So you know that this is our working point where the characteristic curve and the system curve cross each other. And that's where we get our volumetric flow rate as well as the head of the pump. Yeah, so we call it working point. So in a case whereby the system curve and the characteristic curve, they don't even meet, or they don't cross each other. So meaning that you must now extend your readings, your volumetric flow rate readings, up until they cross each other, because the aim here is to get what? Is to get the volumetric flow rate and the pump rate. If, let's say for example, these two curves were not crossing each other, meaning that we were supposed to add or extend this volumetric flow rate readings, meaning we'll have 0.06, 0.07, yeah, maybe till 0.1, maybe up until 0.1, yeah. So eventually they will end up meeting somewhere. So yeah, from our working point, so that's why we're gonna determine the volumetric flow rate along x-axis and the head of the pump head, or rather the height of the pump along y-axis. So this means that volumetric flow rate in this case will be here, will be somewhere here. And then since this is 0.042 and this is 0.044, this means that this is 0.045 and then 0.046, 0.048, then 0.05. This is 0.045. All right, so this means that the volumetric flow rate that we managed to get is equals to 0.045 cubic meters per second. Then let's determine the head. So the head, since this is 28 and this is 39, not 20, yeah, it's 28 and this is 29, yeah, 28 and then 29, then 30, meaning that our head here, since it's in between 29 and 28, our head here is equals to 28.5. Is equals to 28.5. So that is the magnitude of our head. Our head here is equals to 28.5 meters. 28.5 meters. Then we must now determine the magnitude of the power required by this pump. We must calculate the magnitude of the power required by the pump if the efficiency at the operation point is equals to 67%. So we know that the formula for the hydraulic power is given by the specific weight, which is density times gravitational acceleration, times the volumetric flow rate times the head of the pump, and then divided by the efficiency. So let's substitute. The pump is used to pump water. So meaning that we're taking water here as our fluid. So this means that the density here will be equals to 1,000 or 10 exponent 3. Then the gravitational acceleration will be 9.8. Volumetric flow rate from the working point is equals to 0.045. The height of the pump, 28.5 meters, and then divided by the efficiency. So when you are given the efficiency in percentage, you must always divide it with 100%. So meaning that we'll have 67% divided by 100. percent. So meaning percentage, we'll cancel percentage, then we'll be left with this fraction 67 per 100. And then 67 divided by 100 is equal to 0.67. 0.67. So therefore, the hydraulic power here will be equals to 1000 times 9.8, and then times 0.045, and then times 28.5, then divided by 0.67. So therefore the power is equals to 18,758.96 watts. So meaning that this is question 1.1.1, 1.1.2, 1.1.3 respectively. So this is question 1.1.1, and this is 1.1.2, and then this is 1.1.3. Yeah. So that's how to solve this problem. Do you guys have questions?
No, it's understandable.
Okay. Yeah, so this is your graph. And then let's try this with Excel. Let's just quickly draw this graph with Excel. Okay, let me not share my screen. I'll be back. Okay. Yeah, so here's my spreadsheet. I'm sure this Excel of mine won't be the same as your Excel from a desktop or other laptop. Yeah, because I'm not using laptop here, so they will be slightly different. So okay, because here I already have like the whole data, like volumetric flow rate readings, the characteristic curve readings, as well as the system curve readings. So I'm no longer going to do calculations. So in your spreadsheet, first column, you'll have first column, which is column A, of course. You have the readings of the volumetric flow rate given in cubic meters per second. Then second column, of course, you'll have the head readings or the characteristic curve readings, of course, given in meters. Third column, you will have the system curve readings now, given in meters. Yeah, so of course underneath cell A1, of course underneath cell A1, you'll have the readings of the volumetric flow rate up until 0.05 cubic meters. So remember, let's go back to here. So remember, the volumetric flow rate readings are as follows: 0.01, 0.01, actually 0, sorry, then 0.01, 0.02, up until 0.05. Okay. So underneath cell A1, we'll have the readings of the volumetric flow rate in cubic meters per second as follows: 0, and then 0.01, and 0.02, 0.03, then 0.04, then lastly 0.05. So of course, after entering 0 cubic meters per second, you'll press enter to move to the next cell. So you'll have 0, then press enter, then 0.01, then enter, 0.02, then enter up until 0.05. Now, let's enter the ratings of the characteristic curve. So the ratings of the characteristic curve are as follows. So we've got 45.5 followed by 43.1. Okay. So we'll have 45.5, enter. Or let me say underneath cell B1. Cell B1 is this cell. Underneath cell B1, you will have the ratings of the characteristic curve. So meaning that in cell B2, which is this cell, in cell B2, you'll have the first rating of the characteristic curve, which is 45.5. Then followed by the second one, which is 43.1. Then after that, 43.1. 43.1. Then enter. For 43.1, we've got 39.9. 39.9 and then 35.9. Yeah. So we'll have 39.9 followed by 35.9. And then after that, you will have last two already. So it's just 31.1 and 25.5. 31.1 followed by 25.5. Then we are done entering the readings of the characteristic curve. Now let's enter the readings of the system curve underneath cell C1. Underneath cell C1. In meters, so the readings of the system curves or the ratings of the system curve are as follows. So our first rating is 18.5 followed by 19, 18.5, enter, then 19, enter. I saw 20.5 after this 19.5. And then after 20.5, we'll have 23 and 26.55. 23, then 26.55. Then lastly, we'll have 31.1. Sorry, 31.1, then enter. Yeah, so now we have managed to enter all the readings of the volumetric flow rate, head system, and what the characteristic curve respectively. So from here to draw our graph, we will have to highlight everything here. We'll have to highlight all this data. Of course, you'll move your cursor to cell A1. you'll move your cursor to cell A1. And then on the right bottom corner of cell A1, you have to, of course, if you're using mouse, you'll have to press that bottom right corner of cell A1, press and hold, and then drag it all the way to cell C7, meaning to the last cell, to the last bottom cell towards your right hand side here. All right, then after here, after you have highlighted everything here, and now you'll have to go to insert, like on the ribbon of the Excel or spreadsheet, you have to move from head to insert. Okay, so under insert, there will be option for chats. So there will be option for chats. Go to that option, and then under the chats, because centrifugal pump graph is a scatter plot type, so meaning that under the chat you'll have to select the scatter plot, always scatter plot, that one. Okay, and then here, of course, your graph, your graph will have to look like this, meaning you'll have to select this graph here. Your graph will have to look like this. Your graph will have to look like this, because remember initially we had the dots, and then after that we had to join them together. So your graph must look like this. Then from here, you can see that along x-axis I've got here H into M and H system into M. Yeah. From here, I don't want this legends along my x-axis. I don't want this legends along my x-axis. And then from here, which means I'll have to go to elements, and then under elements I'll go to legends. And since I want this legends to be on my right hand side of this graph, then I'll have to select right. Then you can see that now my legends are on the right hand side of this centrifugal pump graph. Now what we showed off here is the x-axis title as well as the y-axis title. So we don't mind about the chat title or the heading of the graph. This one we can remove. We don't worry much about this. You won't get marks for that. I'm just trying to remove it.
So sorry,
Fine.
to interrupt.
Yeah.
I'm trying to highlight the entire information as you said, but it's not highlighting. You said we must go to the bottom corner of the flow rate.
Yeah, and then press hold and then drag your mouse.
Okay, press hold.
Drag
And
your
I'm
mouse
dragging-
to cell C7.
It's not going there. It only allows to go to C1. I don't know what could be the reason.
No, it can't be. Try to force it. It can't be. You can go to you said cell C1.
Yes. You said I should go to the flow rate cell, right?
Yes, which is A1. Yes.
C1, yes.
Yeah.
Then look at the bottom of right bottom and hold. It only allows me to highlight going down instead of highlighting the entire table. I don't know what's the cause. How did you highlight? Let me see again.
Okay, I'm in cell A1, right?
Yes.
And then from here, I'm gonna click on the right-hand side bottom corner of A1, and then
Okay.
drag it all the way to cell C7.
It's not allowing. It's fine. Let's continue. It's not giving me exactly what you're getting.
Okay, maybe. Yeah, I'll assist you after this class tomorrow, of course. Yeah. Okay. Okay. So, like as I was saying, I want us now to have the x-axis title and the y-axis title. Yeah, I want us to have the x-axis title and the y-axis title. And then again, yeah, from here you're going to just highlight your graph, and then from there you'll go to elements, other elements. You'll see you will have axis title, and then go to axis title, please switch off your mic, and then under axis title you'll have primary horizontal and the vertical horizontal. You have to select both of them. So I'm selecting primary horizontal, meaning I'll have my axis title, and then after that I'll go back to elements, under elements, go to axis, and then under axis I'll again select the vertical or the primary vertical. So now I've got the y-axis and the horizontal axis or x-axis. So now let me edit, starting with the horizontal axis or x-axis. Here I've got volumetric flow rate in cubic meters and then per second. And then here I'll have the head in meters. Or alternatively, you can have head in meters / H system / H system, because we are also reading the curve of the system along y-axis. Yeah. So now what are we left with? Oh, so from here we'll have to now add the horizontal and the vertical minor grid lines. Horizontal and the vertical minor grid lines. So again, we'll go to elements, highlighting. Okay, we'll start with highlighting the graph first. Then after that, we'll have to go to elements. And then under elements, we'll go to grid lines. Under grid lines, we'll have to select both the primary minor and the vertical minor grid lines. And then we are done with our graph. So in this case, our working point in this case is somewhere here. Sorry. It looks like I've got only horizontal minor grid lines. Wait. Yeah. Yeah, fine. Let me just copy this graph and paste it here. So this is our working point. This is our working point. So meaning that the volumetric flow rate will be here. So this is 0.04. This is 0.04, 0.05. Meaning that this will be 0.042, 0.044, then 0.045, then 0.046, 0.048, then 0.5. And then the height will be somewhere, this is 25, and then we'll have 25, and then this will be what? 26, actually, 27, 28. Yeah, somewhere 28. 1, 2, 3. This is 25. 28. Yeah, this is somewhere 28.5. 28.5 because this will be 29. I'm not sure if you guys are able to see this minor grid lines. So yeah, volumetric flow rate is still equals to 0.045, and then the height is somewhere 28.5. Yeah, so that's how to draw this thing using an Excel. That's how to draw this graph using an Excel. And then I can see, yes.
I'm a bit confused counting how when you're counting 0.04. So which means you're saying 0.041, 0.042. You're counting like that up until 0.045.
No. 0 point is, okay, this is 0.04, right? So which means after that, because between or in between 0.04 and 0.05, we've got 5 minor vertical grid lines, which are 1, 2, 3, 4, then 5, right? So meaning that since this is 0.04, this will be 0.042, 0.044, 0.046, 0.048, and 0.05. Yeah. You get it?
0.042, 0.0. Oh, okay. Yeah.
So meaning that for the minor vertical grid lines, we're using equidistant scale of 0.002. You get it? So meaning that, yeah, you will have 0.04. Then after that, you'll add 0.02 on this 0.04. Then it will give you 0.042.
Oh.
Yeah. Yeah.
No. Okay, thanks.
Okay. To answer question 1.2.1. So this want us to, or this question actually want us to draw a centrifugal pump graph. We don't have to use graph paper. We You don't have to use Excel, but we can draw this graph using freehand drawing. Yeah. So meaning that for this question 1.2.1, question 1.2.1. Okay, so here they're saying draw a rough graphical representation of a typical single centrifugal pump curve. So here they want you to use a black pen for both question 1.2.1.1 and question 1.2.1.2. So 1.2.1.1. So you must draw a graph of the head available against the flow rate. So the graph of the head available against the flow rate. So the graph of the head available against the flow rate, of course, will look like this. So is the graph with one characteristic curve? Is the graph with one characteristic curve? So it will look like this. So this is the graph of the head available in meters versus the volumetric flow rate.
So should this
Meters per
graph be
second.
in relation with the previous graph that we did?
Come again?
Like this graph that you're drawing, should it be in relation with the previous graph that we did? Or it's something different? Does it have anything to do with the previous graph that we did with Excel?
No, this is something else.
Okay.
Yeah. And then from here on the very same typical single centrifugal pump graph, they want us now to draw the system curve of the pump, which is the head required against the flow rate. Against the flow rate, meaning that wait. So this is 3 marks and then this is 2 marks. Okay, so this now we're gonna draw this separately. So meaning that for the system curve, which is the head available versus the volumetric flow rate again. So I have question 1.2.1.2. I will have the graph that looks like this. System curve of the centrifugal pump graph look like this. So this is the characteristic curve. This is the system curve. Again, this is the graph of the head system available. Head system available versus the volumetric flow rate versus the volumetric flow rate. Yeah. And then lastly, they say here 1.2.2. So we must clearly indicate on the drawing from question 1.2.1 how the curve will change if a second identical pump is connected in series and as well as in parallel. So okay, for question 1.2.1, so if we combine characteristic curve and the system curve, and the second identical pump is being added into the system. And these two pumps now are connected in series. Our graph will look like this. So this is question 1.2.2. And then 1.2.2.1. So combining characteristic curve and the system curve of the single pump. System curve and characteristic curve. So if they add a second identical pump to this single pump, and these two pumps will be connected in series, our graph will look like this. Remember, when the two pumps are connected in series, in order for us to get the performance point or the working point, we must multiply the readings of the characteristic curve by 2 in order for us to get the second characteristic curve of the second pump, or the second pump characteristic curve, meaning we must multiply the readings of the characteristic curve of the first pump by 2, meaning that our graph will look like this. Meaning, since here they're saying I must use blue, so meaning our graph will now look like this, something like this. So multiplying the characteristic curve by 2, the graph of two identical pumps that are connected in series will look like this. Of course, this will be the volumetric flow rate in cubic meters per second, and the head in meters per second slash H system in meters. And when they are connected in parallel, when two pumps are connected in parallel, we have to multiply the readings of the volumetric flow rate by 2 to get the second characteristic curve of the second pump. So meaning that our graph now will look like this. I'm lazy to draw the entire graph. Let me just copy this and paste it. I will remove the second characteristic curve. It's fine. So I'll have the characteristic curve of the first pump, and then since now these pumps are connected in parallel, in order for us to get the second characteristic curve, we have to multiply the readings of the volumetric flow rate by 2, meaning that our graph of the two pumps that are connected in parallel will look like this. Yeah. So that's the difference between the two. Yeah, so that's how to answer this questions, guys. Do you have questions here?
No, regarding this ones, I don't have a question. I managed to highlight the entire information. Now I don't know how do I insert it into the graph.
How to insert the graph?
Yes, after highlighting the entire information, I managed to highlight it.
Okay, under ribbon of the Excel, must you have to go to insert?
Okay, so let me just go back a little bit. So I go to insert after highlight. Do I highlight and copy, or I just highlight and go to insert?
Just highlight and go to insert.
Yes, I just did.
And then under insert, there is chats. Go to chats.
Chats, yes.
And then under chats, of course, you'll find different types of graphs, right?
Yes.
Then you select scatter plot, yeah.
Okay. I selected it.
So does it give you the graph? Or
It gives me
yes.
a plain table that does not have the points.
It gives you that plain table or plain graph.
Plain graph. And
Yeah, that does not have
the points.
And let me help you tomorrow.
Okay, no problem.
Yeah. Let me help you tomorrow.
Okay, no problem.
Yeah, because like I said, I'm not using laptop here. Yeah, so it's a bit different. Yeah. Okay.
All right. No.
Okay. So now I want to dive into the affinity laws. I'm not sure if you have done this already. Affinity laws. With this 30 minutes remaining, I want to dive into affinity laws. So affinity law of the centrifugal pump graph actually it states that is the relationship of what? Is the relationship of the capacity, which is the volumetric flow rate, the power, and the head to the impeller speed and the diameter. So that's the law of affinity. So it states that is the or let me say the affinity law, it expresses the relationship of the capacity. We're talking about the volumetric flow rate, the head, of course, which is the height of the pump, and what the capacity, the head, and the power, to the impeller, of the centrifugal pump, to the impeller speed. And of course, speed is in what here? Is in capital letter N. Yeah, it's represented by capital letter N in revolutions per minute. And what else? And the diameter. And the diameter. Yeah. So this is the law of affinity. Affinity laws of the centrifugal pump graphs. Yeah. So the reason why we need affinity laws is that when the characteristic curve of the second pump added into the system is not available, we can use the readings of the first centrifugal pump to find the readings of the characteristic curve of the second pump. So that's the reason why we introduced this affinity laws. So the reason is, when the characteristic curve of the second pump, it doesn't matter whether it's connected with the single pump in series or parallel. So we want to utilize the readings of the first pump to be able to find the readings of the characteristic curve of the second pump. So that's the reason why we introduced the affinity laws. So under these affinity laws, we've got this formulas. But before I start with the formulas, these are what we call characteristics of the pump: capacity, the head, and the power. So these are what we call the characteristics of the pump. Pump characteristics. Let me add them here. So the characteristics that we have for the pump are capacity, the power, and as well as the head, of course. Capacity, like I told you, is the volumetric flow rate. So these are pump characteristics. So whenever, according to affinity laws, whenever the impeller diameter is constant, these are the formulas that we get from the affinity laws. So whenever the diameter is constant, the impeller diameter is constant, this means that both, or actually all the characteristics of the pump are directly proportional. So are directly proportional to the impeller speed, because here we're talking about the diameter that is constant. So this means that the capacity is directly proportional to the impeller speed. So if the capacity is directly proportional to the impeller speed, remember impeller speed, I said, is measured in revolutions per minute, and the capacity is measured in cubic meters, of course, per second. So if the capacity is directly proportional to the impeller speed, this means that the volumetric flow rate of pump number 1 divided by the volumetric flow rate of the second pump will be equals to the impeller speed of pump number 1 divided by the impeller speed of pump number 2. When the volumetric flow rate is directly proportional to the impeller speed. Yeah. So if the pump of these two, not the pump, but the diameter, the impeller diameter of these two pumps are equal in sizes. So meaning that if you increase the volumetric flow rate in the first pump, the impeller speed will also increase. If you decrease the volumetric flow rate in the first pump, the impeller speed of the first pump will also decrease. That's why I'm saying that the volumetric flow rate here is directly proportional to the impeller speed. Same applies to pump number 2. If I increase the volumetric flow rate of the second pump, its impeller speed will also increase. And if it decreases, this will also decrease. Then, this is the formula number 1. When diameter is constant, when the impeller diameter of these two pumps are equal. So when the impeller diameter is constant, this is the first formula that we get under affinity laws. The second one, is that we spoke about the capacity. Now let's talk about the height. Yeah. So with the height, is that when head number 1 divided by head number 2. Wait. So let me repeat again. If the diameter is constant, this means that this means that the head will be directly proportional to the impeller speed as well. And this means that head of pump number 1 per head of pump number 2 will be given by. So this time around, we'll have the impeller speed of pump number 1 squared divided by the impeller speed of pump number 2 squared, being equals to the heads of these two pumps respectively, pump 1 and pump 2. And then again, the third one is that when power is directly proportional to the impeller speed, power required by pump number 1, power required by pump number 2 will be equals to the impeller speed of pump number 1 cube divided by the impeller speed of pump number 2 exponent 3. So this is where only when the diameter is constant, meaning that the impeller diameter of these two pumps are equal, or the impeller diameters of these two pumps are equal. So then if now the impeller speed is the one that is constant, if the impeller speed is constant, yebo, I'm listening. Policy, I'm listening. Okay, let's proceed. So, if I was saying that if the impeller speed is constant, yes, go ahead. No, I can't hear you. Are you guys able to hear him?
No.
No, sir.
Okay. Yeah, maybe. Yes, he raised up his hand again. Just send a WhatsApp message to me Because I can't hear you. Let's proceed. So I can see that time is no longer on our side, but after this, we'll just have one example of this, and then the rest you'll solve them on your own. So which means that next time when we meet, we're gonna have to discuss this last three examples here. Okay, so I was saying that now since the impeller speed is constant, remember the laws of infinity, it expresses the relationship of what capacity, the head and the power to the impeller, diameter and the speed. So meaning that only these two parameters must be constant when coming to the laws of infinity, the diameter, impeller diameter, or the impeller speed. So if the impeller speed is constant, again we'll have the volumetric flow rate, which is characteristic number one, first, or one of the characteristics of the centrifugal pump, being directly proportional to now the diameter, because the impeller speed is constant. The impeller speed is constant. And if volumetric flow rate is directly proportional to the diameter, this means that we'll have the volumetric flow rate of pump 1 per volumetric flow rate of pump 2 being equals to.
Hello?
Yebo, I
Hello?
can hear you now.
Okay. Yeah, no, I'm sorry about that. Nakinali challenging yana ya ntwena microphone. No, the question I wanted to ask Mener was that when we're doing this question, the first thing that Mener showed us was that Q2 is equals to Q1 and N2 is equals to N1. So I wanted to understand, does this number say 2 gets to be godimo, 1 gets to be class? Does it have any impact, or it doesn't matter whether you've said Q2 or what? Because the example you showed us, mainly Q2, N1, H2, P2, which were all two. Yeah, thanks.
No, it doesn't matter. This Q1 divided by Q2 is equals to N1 divided by N2 is the same as Q2 per Q1 is equals to what? N2 per per N1, yeah. Sorry, per N1, yeah. Q2 per Q1 is the same as Q2 per Q1 is equals to N2 per N1. Or Q1 divided by Q2 is the same as N1 divided by N2. Same thing, doesn't matter.
Okay, thanks so much, Bella.
Okay. So yeah, if volumetric flow rate is directly proportional to the diameter, then we'll have this. And then secondly, the impeller speed is constant. And then in terms of the head versus the diameter or the impeller diameter, we'll get this formula. We'll have the head available in in pump 1, the head available in pump 2, which will be equals to impeller diameter of pump 1 squared per impeller diameter of pump 2 then squared. And this means that even here, the head is still directly proportional to the diameter because the impeller speed is constant. Then number 3, power versus the impeller diameter. So again, if the impeller diameter is if the impeller speed is constant, This means that power will now be directly proportional to the impeller diameter. And this means that power required by pump 1, power required by pump 2 will be equals to impeller diameter of pump 1, then exponent 3 divided by the impeller diameter 2, then all exponents 3. So that's according to the affinity laws. That's according to affinity laws. So you must know these formulas. So like I said, this is diameter, sorry. This is diameter and is in meters. This is the capacity or the volumetric flow rate is in cubic meters per second. N is the impeller speed. Impeller speed is measured in revolutions per minute. And then this is the head available, the height of the pump, of course, in meters. And power, of course, is in watts. Yeah, so that's what you have to know about the affinity law. So normally when coming to affinity laws, you will be given, for example, the volumetric flow rate of the two pumps, including one impeller speed of one of these pumps, and then they'll want you to find the impeller speed of the other pump. Yeah. In most cases, you'll be given 3 things, or they can give you 2 of these impeller speeds, including one of the volumetric flow rate, and you'll have to find the other volumetric flow rate. Like I said, I'm just gonna go through example number 1 here, which is question 9. So the rest, please go through them, and then I will go through this next week with you. Do you guys have questions based on this? Okay, so let's quickly answer this question 9 here. So in question 9 here, they're saying that a centrifugal pump that rotates at 1,400 revolutions per minute delivers a capacity of 0.015 cubic meters of water per second at the height of 100 meters. So these characteristics are the or let me say the head and the capacity and the impeller speed are the characteristics of this centrifugal pump. So then here they're saying that the speed of rotation is increased to 1,700 revolutions per minute. Then you must calculate the new discharge head and the power if the efficiency stays the same. If the efficiency stays the same. Okay, so meaning that here we've got the impeller speed 1, capacity 1, as well as head 1. So here you must calculate new discharge. New discharge meaning you must calculate Q2 as well as the head 2 and power 2. So let me just write this down. we're given the first impeller rotation speed of 1,400. Revolutions. Actually, is RPM. Yeah, revolutions per minute. We are also given the capacity, the volumetric flow rate of 0.015 cubic meters per second. cubic meters per second, as well as the head of 100 meters, first head of 100 meters, including impeller speed 2. If the speed is increased to 1,700 revolutions per minute, then we must calculate the new characteristics of this pump. 1,700 revolutions per minute. So what is the volumetric flow rate 2, head 2, and power 2. So since we're given the magnitude of the impeller speed, meaning that in this case the impeller diameter remained constant, meaning that the diameter doesn't change. The magnitude of the diameter doesn't change. So to find the volumetric flow rate, which means we'll have to use this formula, Q1 divided by Q2 is equals to N1 divided by N2. We're looking for Q2. Q1 is equals to 0.015, N1 1,400, N2 1,700. Oh, this is 9.1. Question 9.1. So because we're looking for Q2, a new discharge or capacity or a volumetric flow rate, of course we'll have to cross multiply. Then we'll end up having Q1 N2 is equals to Q2 N1. Because I'm looking for Q2, I'm going to divide both sides by N1. So this means that Q2 will be equals to Q1 times N2 divided by N1. And then let's substitute now. So the volumetric flow rate, first volumetric flow rate is equals to 0.015. Then the impeller diameter, impeller speed, the second impeller speed is 1,700 revolutions per minute, whereas the first impeller speed is 1,400 revolutions per minute. So therefore, the new volumetric flow rate, if the speed increases, the new volumetric flow rate will be equal to, of course, since I mentioned that since the volumetric flow rate is directly proportional to the impeller speed, meaning that if you increase the speed, the volumetric flow rate will increase. So yeah, this is what we're gonna prove now. This is what we're going to prove now. So you can see that the first volumetric flow rate was 0.015, meaning that it must be above that now. The new volumetric flow rate must be above this 0.15. Let's see. So we've got 0.015 times 1,700 per 1,400. So that is equals to 0.018 cubic meters per second. So you can see that Q2 is greater than Q1. And then from here, they want us to find a new head, pump head. If the speed increases, again here, the head is still directly proportional to the impeller speed. And if you increase the head weight, if you increase the head, the speed will increase, or vice versa. If you increase the speed, the head will also increase. Yeah, because they're directly proportional to each other. So here, since diameter is constant and the head is directly proportional to the impeller speed, meaning that H1 per H2 will be equals to N1 squared per N2 then squared. So we'll use this formula. So this is 9.2. Okay, so we're looking for the new head, meaning that we'll have to cross multiply. This is the same as H2 N1 squared is equals to H1 N2 then squared. We're looking for H2, so meaning that we'll have to divide both sides by N1 squared. So therefore H2 will be the same as H1 and then times into N2 squared divided by N1 squared. So let's substitute. Our new height was equals to 100 meters, or our initial height was equals to 100 meters. So since head is directly proportional to the impeller speed and the speed has increased, this means that the head must also increase. Okay, let's substitute. This is the same as okay, N2 squared divided by N1 squared. Well, it's the same as N2 divided by N1 all squared. So N2 is equals to 1,700 revolutions per minute, whereas N1 is 1,400 revolutions per minute. This means that new head here, squared, I forgot squared. Or alternatively, this is the same as, this is the same as what? Alternatively, this is the same as 100 times 1,700 squared divided by 1,400 squared. Yeah. So that is equals to, I don't know. I must also change the volumetric flow rate, sorry. So that is equals to 147.5 meters. Yeah,
Our square only once more, and the more it's a D square, 1.7 square, 1.4 square. But if you calculate here,
It's still the same.
it's the
Yeah.
same.
Yes.
Yeah.
Okay, sharp.
Thank you. Last one. We must find power now. New power, of course, diameter is constant and power is still directly proportional to the speed. If you increase speed, power will also increase. Let's see. So 9.3 Since power is directly proportional to the impeller speed here, so which means we'll use this formula. We'll have first power divided by second power is equals to impeller speed 1 cube divided by impeller speed 2 cube. I'm looking for power 2. Of course, I'm going to cross multiply. So I'll have P2 and 1 cube is equals to P1 and 2 cube. I'm looking for P2. So which means I'll have to divide both sides by N1 cube. So therefore P2 will be equals to P1 into, I forgot cube here. P2 will be equals to P1 into N2 cube divided by N1 cube. Yeah. So the first power here was equals to what? Oh, we don't have power here. Okay. So since we don't have the magnitude of the power now, we can use this formula because the efficiency also remains constant. Yeah, because the efficiency also remains constant. So we can use this formula. Sorry, I didn't see that we don't have power. We know that the hybrid power is given by density times gravitational acceleration times volumetric flow rate and then times the height. Divided by the efficiency. So if the efficiency remains constant, which means that we're not gonna have the efficiency. This means that efficiency of first pump is the same as the efficiency of the second pump. So meaning that we're not gonna have efficiency here. So we can remove this, meaning that efficiency is the same as 100% in both pumps. Right, so from here, let's assume that we're not assuming this centrifugal pump is delivering water. It's delivering water from one point to another. So the density that we're going to use here is 1000 volumetric. No. The gravitational acceleration 9.8. Sorry. Then volumetric flow rate and the height. Since we're looking for the new power, since the speed was increased, we're going to have to use the new volumetric flow rate, which will be what? Q2, and then multiply by the new height, which is H2. Okay, so our new volumetric flow rate is equal to 0.018. Whereas the new height is equal to 147.5 meters. So what will be the new power since the impeller speed was increased? So that will be equals to 26,019 watts. 26,019 watts. But they said this power must be in kilowatts according to this question. Yeah, it must be in kilowatts. We must calculate the new power in kilowatts. So of course, to convert this power from watts to kilowatts, we'll have to divide this 26,019 by 1,000 or multiply it by 10 exponent negative 3. So that is equals to 26.019 kilowatts. That's it. So, okay, this is power 2 since the speed 2 or the impeller speed was increased. So meaning that if we want to calculate power required by pump 1, so which means that you're going to use this formula since the efficiency remains constant or stays the same. And then when coming to capacity or the volumetric flow rate, you'll use Q1, the magnitude of Q1, and the head you'll use the magnitude of the magnitude of H1, sorry. Yeah. So that's how it works.
So now, meaning according to this question, we were looking for the new power, which is P2.
Yeah.
So when we're looking for that, we'll have to use the new volumetric flow rate and the new height.
Yes.
Okay.
Yeah.
And in case the power is given,
In case the power is given, meaning that you have to use that formula of P1, the P2 is equals to N1 cube, yeah? N2 cube, yeah, if the power is given.
so let's say it was never stated that it should be in kilowatts when the power is given, so we must just leave it in watts.
Then you are gonna leave it as 26019.
Okay.
Yeah. Okay, guys, let's stop here. Let's stop here. Like I said, please answer just 2 questions here. And this one as well. Let's stop here. I thank you.
Thank you, sir.
Thank you.